And with that, I think let's just get rolling. So a couple of quick things. The first one is, please mute your microphone while Rich is speaking. If you have any questions, please hold them until the end, unless it's one of those really burning questions you have to ask right now. And in that case, just type it into the chat and we'll get to it in the Q&A session. With that, let's welcome Rich and thank him for joining us today. Rich, just to give everybody a little bit of background for him, he did his bachelor's at the University of Gloucestershire, and he finished that in 2008. I finished a master's from the University of London in 2009. And then he moved to the Southern Hemisphere and finished a PhD from Victoria University of Wellington in 2015. Then he moved back to the Northern Hemisphere. This man's a globetrotter, if you will. And he did a postdoc at the University of Durham. And then he's come back to the Southern Hemisphere, and he's a postdoc currently at Monash University, where he was just recently awarded a Decker Fellowship. So congratulations on that one. And the title of his talk today is The Impact of Glacial Isostatic Adjustment on Cosmogenic Surface Exposure Dating. So take it away, Rich.
Thanks, Ross. Yeah, so I actually just a second ago changed the title slightly because this is talks about some work I did when I was based at Durham a couple of years ago, and it was mainly focused on surface exposure dating, but actually the impacts kind of are beyond just that particular kind of type of application, and really, I guess for this community, the nuts and bolts is the impact specifically on nuclide production. And so this is, generally we're looking at what's called glacial isostatic adjustment. So this is where you've got some vertical deformation of the land surface as a result of mainly large continental ice sheets. And so this kind of background figure here is really highlighting those effects at the LGM, and really you will see an effect on, kind of cutting to the chase, you will see an effect on nuclide production wherever there's a color, so whether it's purple or whether it's orange, and the only places that avoid this effect is where it's white. And so just kind of jumping into it, obviously we all kind of use cosmogenic-nuclides in some way, and in particularly for the work that I do, it's mainly looking at glacier ice sheet history, and so we can directly date glacial landforms and deposits, and then use that to reconstruct lateral and vertical extents through time. This is a nice photo. I think that's Kevin and Sean standing on that boulder there in New Zealand. And then this data can be used to constrain ice sheet modeling. So here, just showing an example for Antarctica, where pretty much all the constraints on ice thickness change through time are from cosmogenic-nuclide exposure dates. And then we also have, say in here, and kind of Scandinavia, Northern Europe, again, the key constraints on ice sheet history, but in this case, they're kind of horizontal constraints from cosmogenic-nuclides. But actually, it's beyond just this particular application. And just showing here, we've got sample dates from the Octopus database of erosion rates from beryllium 10. And you can see that actually there's a lot of samples, particularly in kind of North America and Europe, which are in this area just beyond the ice sheet margin, essentially, at the LGM. And again, these are regions of the planet which can feel this effect from glacial isostatic adjustment, which I will shorten in this presentation to just called GIA. And as we should all be familiar with, the kind of cosmogenic-nuclide production is dependent on altitude. So obviously we've got the cosmic ray hitting the top of the atmosphere. We've got the protons, neutrons, secondary kind of particles that cascade through the atmosphere, and this energy is lost as it passes through denser and denser atmosphere. And so production is very much dependent on the atmospheric depth and therefore atmospheric pressure. And so as a result, we're going to get much higher nuclide production at higher elevations than we are at lower elevations. And so this is where this GIA and the effect of land surface change through time is going to potentially play quite an important role. And so here I'm just showing kind of a GIF that will hopefully repeat itself. This is modeled land surface elevation change since the last glacial maximum. And so we've got a map of the change here. And so we've got where the land is depressed by continental ice sheets in purple. And then in orange, we've got what's referred to as a peripheral bulge. So this is where the land surface actually elevates because of the movement of the mantle from beneath where you've got that depression out to the sides. And so, yeah, so you have elevation change both where there's an ice sheet and beyond the ice sheet. And so there's 3 sites here that are picked out that have contrasting elevation histories. So we've got one from North America, which is sat at this peripheral bulge. So you can see that tracking through time. We have one which is in England, kind of South England, which is pretty much uniform through time. It's kind of sat in that zone between the ice sheet and the peripheral bulge. And then we have a region in Scandinavia where you've got fairly significant depression of the land surface through time. And obviously, yeah, the peak is around the last glacial maximum, and then everything comes back to normal at present day. And the key takeaway from this is that this GIA effect is both spatially and temporally variable. And this is dependent on the ice sheet change, kind of at a regional global scale, and also the rheology of the solid Earth. And there's been a few studies that have tried to have a look at how GIA will affect nuclide production and therefore surface exposure ages. But this has kind of been done very much on a local kind of study site scale. And so the purpose of this study was to kind of systematically assess this effect on nuclide production kind of at a global scale. And obviously kind of assess the implications for surface exposure dating, which also kind of carries through to kind of erosion rate studies as well. And so the general approach we applied here was, first of all, we used the output from a GIA model. So I won't go into the details of this, partly because that's not my area of expertise. But we used a fairly recent model, the I6G, which is considered, yeah, kind of a pretty good, kind of most kind of up-to-date GIA model that's at a global scale. And then also kind of used, obviously need to use a scaling model as well. And for this, we used the Nat Lifton's LSD, time-dependent scaling model. But all of these scaling models actually assume that you have equal atmospheric pressure through change. You have constant atmospheric pressure through time, and that does not change at all. So had to essentially modified all of the different scaling models, but particularly just focusing on the LSD one here, in order to actually include these time-dependent changes in atmospheric pressure. So the first thing looked at was the impact on nuclide production since the LGM. And this was done by calculating nuclide production in different time slices and looking at the difference between that nuclide production counted for, calculated for modern surface topography, which is what pretty much everyone uses, with the assumption that the land surface has not changed through time, and then also a land surface which has been corrected for GIA, this glacial isostatic adjustment. And so here showing 20,000 years ago, 15, 10, and 5,000 years ago. And the colors here are depicting the production rate relative to present as a percentage. And so we see that in the blues, this is where your production rate has decreased relative to present for that particular time slice, and in red is where the production rate has increased relative to present. And you can see that this pretty much mimics what we see quite closely, not surprisingly, with that GIF I showed earlier with the GIA pattern. And also just kind of picking out here, the bold line is the 10% difference, and the dashed is the 5%. So you can see that, yeah, for these different time slices, there are some quite large areas, and particularly important for those areas that are actually reconstructing ice sheet history, but also that concern studies relatively near the ice margin of both decreased production over 5% and increase over 5%. And yeah, there's a difference spatially through time, and this obviously decreases towards present. And also kind of to pick out, there are some areas here that as the ice sheet retreats, the land surface is obviously going to, the vertical deformation is going to change. So there are some sites that might have been depressed by the ice sheet at one point, and then as the ice sheet retreats, they then come into this area of the peripheral bulge. And these plots here are just highlighting those same sites that we saw earlier. So there are three contrasting sites, and this one is, we've got the time on the x-axis, and we've got the elevation relative to modern on the y-axis, and then we've got the uncorrected versus the corrected. And so obviously uncorrected is what everyone assumes, there's no elevation change through time. And then for these different sites, we can actually see if you use the GIA corrected elevation, that they do either increase or kind of decrease through time. And this is on this plot is the same, but with on the y-axis, we've got the site-specific production rate. And so again, you can see the difference in production rate between the different sites as a result of this difference in the elevation. And so the next thing we did was to actually have a look at the production rate calibration sites, because obviously this is incredibly important. We need to be able to know kind of what the production rate is, and obviously if this GIA is going to affect what we consider to be the production rate, then that could have kind of quite wide implications. So to do this, we had a look at the 6 primary beryllium 10 calibration sites from the Borchers et al. Paper, and again kind of looked at that nuclide production with and without the GIA corrected land surface, and calculated this through time since that independently true age of the site, whatever that was based off, quite often radiocarbon. And so here, just plotting that data, so each of the symbols represents a different sample, and you can see these are split into the different calibration sites, and just showing the kind of the distribution in the map up here. And so we've got the 1-to-1 line, which is solid, which is essentially there's no difference in the time averaged production rate, whether you use a modern or a GIA corrected surface. And then the average for these sites is in the dashed line, which actually sits only just above. And so it's actually quite reassuring that there's pretty much a negligible effect from GIA on the production rate calibration sites. And that's because all of these sites are sufficiently distal from these large continental ice masses. There's the PPT one here in North America, which deviates slightly more than the others. which is hard to say exactly why, but there's also some unaccounted for local GIA effects that might also actually just bring that closer. But overall, we can be quite happy that these primary calibration sites are unaffected. So now we kind of progress using what we consider the present day, or the kind of unimpacted calibration data, and then we use that together with the GIA corrected elevations for all samples that I could get from around the world. And so for this, I used Jacob Hyman's compilation, and again calculated the kind of essentially the normal exposure age, assuming we just got modern elevation, and then an exposure ages that were corrected for GIA. And these kind of this figure presents some of those kind of selected regions of interest. I included New Zealand because it's still important. It's good to have these southern hemisphere sites, as well as Patagonia and Antarctica. So ice was included for New Zealand, but obviously the ice that existed in New Zealand at the LGM is nowhere near the same as what we get for these large continental ice sheets, or even the kind of the Patagonian ice fields as well. And the effect here is pretty negligible. But if we look in other areas of the world, the effect is quite significant. And so what we see here are the size of these circles represent the magnitude of that age correction between the uncorrected using modern elevation and the GIA elevation. And then the color represents whether the age is whether this correction makes the age older or younger. So older ages are going to be where the nuclide production is reduced, and so that's in the region of these continental ice sheets. And then beyond the ice sheets in this peripheral bulge region is where we're going to have a slightly increased nuclide production, and therefore a reduced exposure age. And so those are the ones in blue. And for the purpose of this, I didn't actually go through every single sample, because there are thousands and thousands here, to assess which are considered reliable or not. So what is plotted up here does definitely include some samples that are considered outliers, likely that includes some level of inheritance. But to try and test this a little bit further, we focused in just in the Scandinavian region and went through all the data to try and work out which were outliers or not. And when removing all of those that were considered unreliable exposure ages, we still end up with a maximum age correction of over 2,500 years. So that's still pretty significant, and I'd argue something that needs to be considered more carefully, particularly in this region. And then also kind of globally, we see beyond the ice sheet margin, there's still corrections of up to 1,000 years. And I should say that this, like what was seen before, the kind of the magnitude of this effect, and whether it's the exposure age is made older or younger as a result of accounting for GIA, varies spatially, obviously, but it also varies through time. So again, like I was saying before, there were some regions which were once depressed by a nearby ice sheet, but then as the ice sheet retreated, it then became into this region of kind of the peripheral bulge, so it became elevated. And so it kind of depends on when that exposure age, when that sample became exposed, as to whether it primarily experienced a younger or an older correction. So you can see in this kind of area of North America here, we have samples that are kind of overlapping in location, but some are blue or some are red. And so another way to kind of try and assess this impact is to try and put it in another perspective, is say relating it to a real world case of some exposure ages. And so, for example, here we have a site where we have kind of four example exposure ages, and then we've got the summed probability, and the mean and standard deviation is highlighted by these dashed lines. And then say if we take a fairly extreme snow cover correction, so I think in this case it's about on average 20 centimeters of snow cover, then this will make the exposure age slightly older. So you can see the green curve has shifted. But then if we take account of the more kind of extreme GIA corrections, then first of all, where we have these sites that are in the kind of vicinity of a large ice sheet, and you've got over 2,500 years correction potentially. And then if we've got those areas that are beyond the ice sheet margin, but in the peripheral bulge, again, that can make the exposure age younger by 1,000 years or so. And then when you kind of look at this spread, you kind of start thinking about what is kind of really important to your site and what you need to consider when you evaluate your surface exposure data. I also just chucked this in just now because I noticed this paper came out a couple of weeks ago. So the topic isn't necessarily important, but the fact is in here, for this study, they used the GIA corrected exposure ages that I calculated in the study, and used them to say that actually they fit better with their hypothesized model of Antarctic ice sheet change. So you can see the exposure ages here, and these are GIA corrected ones, and the model that they use here that fits the data better are these, the dark blue and kind of lighter blue-green line here. But they, annoyingly in the paper, they don't actually acknowledge that these are GIA corrected, or the fact that there are added uncertainties to these corrections. But at least it's interesting to see that actually the GIA corrected exposure ages do seem to match better with some kind of external data, model data. But as I said, there are some added uncertainties and considerations for these GIA corrections. So one of those, as I mentioned at the start, is mantle viscosity. And so to evaluate the effect of this, just focused in on Antarctica, because that's my region of interest, and had a look at, we've got Antarctica with a weak mantle viscosity and a strong mantle viscosity, and then we've got the difference relative to present in the production rate, and this is the kind of standard deviation between the two, and there's generally a less than 1% difference. So although this does have some sort of effect, it doesn't seem to be that significant. But what is significant is the ice model you use. So in Antarctica, there are various different ice models used to constrain the GIA model. So there is some circularity in this that I'll get onto again a bit later. And so you can see the difference here, that's in the vertical deformation, and then the corresponding difference in the production rate. And so depending on which ice model and therefore which GIA model you use, you can get up to 15% difference for the LGM time slice at least. And then this plot, again, just highlights the difference between the two. So we've got the general uncorrected age along the x-axis, so from around the LGM down towards present. And then we've got the mean age correction for the two different GIA ice models here. And so you can see that there's quite a bit of deviation, particularly around the LGM, which is obviously then going to significantly affect your age correction. And something else that is not included in this is time-dependent changes in atmospheric pressure. And this was looked at in 2007. And again, you can see there's a spatial kind of pattern that is related to ice sheets. And this was just done at the LGM. And it was a maximum of about 10% difference. And so this effect isn't necessarily as large as the GIA effect. And again, like I said, this is 10% at the LGM rather than as an average since the LGM. But actually if we account for this as well, depending on the location, it may actually either enhance the GIA effect or reduce it. And so this is something that needs to be better considered in combination with the GIA. So to kind of summarize this GIA, which I keep referring to, glacial isostatic adjustment, can actually have quite a large effect, making exposure ages older or younger. And in some cases, particularly close to large ice sheets, this can actually make ages over 2,500 years older. As I just said, the atmospheric change, as well as the ice history model that's used to constrain the GIA, could amplify or reduce the impact from GIA. And really, this is kind of trying to point out to people, really, that this can have quite large implications on your chronologies. And how you how you use your chronologies, particularly from these regions that are influenced by GIA. And so if I was to provide some advice going forward, if your site is in the region of these large GIA changes, I would say that it's very important to evaluate the potential impact, whether or not you use the absolute correction or not. Some studies have looked at relative sea level records to try and constrain locally, but generally these records are not taking account of the full picture and likely underestimate the effect. It's also, as we've seen, this effect varies through time. So it's important to use time-dependent correction. And I guess that for interpretation, the main thing here is if you do see that there's any sort of potential impact at your site, just to be careful about how you interpret your data relative to, say, centennial in particular, and perhaps even millennial scale climate events. That is relevant. But there's still kind of some future challenges. So one of these, as I mentioned earlier, is this circularity. So obviously, to correct surface exposure ages for GIA requires a GIA model, and that GIA model is dependent on the ice model that you put into it to calculate obviously the depression. And that ice model itself, and quite often, is constrained by cosmogenic ages. So if we're kind of going on into the future and really thinking about how we best tackle this, we have to think carefully how we use these models if they're primarily constrained by cosmogenic ages, which we're then saying are influenced by GIA. And also, we still need to systematically assess the combined impact of GIA and atmospheric change. And like I said before, atmospheric changes may amplify or reduce the effect. So we don't necessarily have reliable absolute corrections from just GIA alone. And then, if you want to read more about this, this paper was published nearly 2 years ago now in QSR. And also, if you want to actually play around and evaluate how your data may be affected by elevation change, you can use the ICT if you aren't already familiar with this. We've got a tool here to correct for elevation change. And you can look at different scaling models and also different GIA models. And it also includes a linear rate of change as well, which might be useful if you're thinking about, say, long-term uplift or subsidence, and you've got some estimates of linear rate of that. And this is obviously away from GIA. So you can also account for elevation changes via that as well. And I'll leave it there. Thanks for listening, and I'll take any questions.
Nice, very nice, Rich. Thank you for that. Do we have any comments, questions, my good friend?
Did that all make sense then?
Yeah, that was really good. I thought that was a really good talk.
Right, Russ, can I ask a question?
Yeah, go for it, David.
Yeah, I haven't got the video on for whatever reasons because I don't look too good this morning. Now, just a quick clarification. On the extreme 2.6 kiloyear shift, was that the I6G or the W12 ice sheet model? Because they gave very different results at LGM. That's just to find out what the answer to that one is. That's not my question, though.
Yeah, so that's that was using I6G,
which gave the maximum problem at LGM.
Yeah, so for when I assess the W12 is only for Antarctica. So that's why I kind of partly focus on Antarctica, because there are more GIA models there than there are global models. Can
I reverse the whole argument then by saying that there are a number of good cosmosites for terminal moraines at ice sheet retreat, Laurentide, Fennisconian, Northeast America, Northern Poland. And they have proxy data for paleoclimate change. In other words, there are ancillary supportive data which backs up, based on radiocarbon and independent chronometer, that the cosmo ages of exposure, if you do the outliers in some of the papers, match the paleoclimate interpretations. So everybody's happy that the cosmo ages are saying YD rather than saying LGM, or they're saying AM, not saying anything different. So if you applied your model there, you'd have an extra constraint to pick out which of the ice sheet models gives you the correct GIA. So rather than question the cosmo ages, you select those cosmo ages which are supported by paleo proxy data to be reliable within, let's say, 1,000 years in the deglaciation sequence, and see whether that can tweeze out any fine tuning on the GIA. In other words, it basically reverses the argument. You take a subset of your data, the cosmos, pick those that everybody's happy with because they match the paleoclimate interpretation from other proxies based on radiocarbon or based on VARs, etc. And therefore you can say that the cosmo ages, given a certain scaling, fit within 1,000 years, less than your extreme changes between the two ice sheet models. And that's one point. The other one was, if what you're saying is correct, the debate with the cosmo-Antarctic deglaciation post-dates or predates the meltwater pulse 1A is still now revitalized, because you're putting all the Antarctic ages, given that they're in the depression and the production rates are lower, you would push all the Antarctic ages at 2,000, 1,000 years older, which would make them match with meltwater pulse A at 15,000 years, rather than at 12 or 13,000. And the last comment you made, probably the most important, millennial scale cosmogenic ages really need to be looked at carefully. There's a summary paper by Belko who really qualifies that when you look at millennial scale differentiation of interhemispheric glaciations between 24 and 10,000 years, it's really dangerous grounds to make 1,000 year millennial scale differentiation between timing. And that's a very important point. And your GIA stuff amplifies that even more. You know.
Yeah, I'll try and take those in turn. I guess, the first one, I agree. In a way, that's kind of just highlighting one of the added uncertainties that maybe we didn't fully appreciate before. But there are obviously other uncertainties associated with every site, related to erosion rates or snow cover or whatever, which if you kind of add up all of these, yeah, I agree that certain kind of interpretations related to centennial millennial scale events, you just have to be very careful about it. And I'm sure most people are, but yeah, it's just tricky ground, and I think we kind of have to accept as a community there are these added uncertainties, and just be very careful when we're trying to make interpretations at that time scale. Mm-hmm. Related to the first point, I agree that there are probably more systematic ways in order to further look at this, and maybe that's a good way going forward. I didn't want to do it too much at this stage because, like I said, there's the absolute correction is likely to be slightly different because of these atmospheric changes. And hopefully we can move forward soon on that. I did talk to Nat Lifton at EGU 3 years ago now, and he was actually doing something similar to this, but more focused on the atmospheric changes.
Would that be looking at lapse rate variations at transition, where atmospheric temperature gradients are much more amplified because you're at a transition between cold winds or warmer temperatures? And is that how you're relating it to atmospheric pressure through a lapse rate change? Is that the key, or there's more complications to that?
I recommend you kind of have a look at the Steiger et al. Paper from 2007 that talks about the different effects. There's a couple of different ways that atmospheric pressure can influence production rates, and yeah, it's related to how the density of the atmosphere changes, and to do with the temperature of the atmosphere, so similar to what you're saying with lapse rates. And there's also localized effects to do with katametic winds as well, that in the regions near ice sheets can also then affect the local atmospheric pressure. And yeah, the best way, similar with this, is to actually look at try and use climate models and the atmospheric changes from those in order to constrain these changes through time. But again, we also then get with the circularity, because those climate models, in order to have these effects of atmospheric pressure change, are hugely influenced to where you have ice sheets and the size of those ice sheets, which are again partly constrained by cosmogenic-nuclide data. Although I think with the climate models, the exact dimensions of the ice sheet probably have a slightly less effect than that on GIA. But again, it's just a circularity to consider going forward, and I don't have any answers for that. We did, for this paper, we did have a few sites where we had a look at the interpretation of those sites and how this correction might play in with that. And to some degree, they do fit and some not, but it wasn't a systematic assessment of various different sites, and like you were saying before, kind of almost going backwards, assuming that those sites are potentially right, with independent data, and therefore using those sites to then constrain the uncertainty on the GIA correction. That's something I haven't done. Okay. And then also on the other points related to Meltwater Pulse 1A, I did actually have a look at this, and there's also, I did discuss it in the paper as well, actually. But this, so for those people that don't know, there's a lot of sites around Antarctica that show rapid ice loss from cosmogenic data in the kind of early Holocene. And if you include a GIA correction, even the more extreme one from the W12 model, that does shift the exposure ages a couple of thousand years older, or up to a couple of thousand years older, which gets it closer to Meltwater Pulse 1A. But still, the majority of them are still come after Meltwater Pulse 1A. So it's pushing it more to that realm if we assume the more extreme situation. But I don't think we can say yet that by accounting for this effect, we suddenly can say that Antarctica ice loss all happened during Meltwater Pulse 1A.
So we still have a debate.
Yeah, there's always debates. Yeah. In fact, the more science comes out, the more the debate continues.
Well, one of the added points you should keep in mind when one does debate this meltwater pulse 1A, it gets very sensitive actually between two teams. It's like the stabilists and the non-stabilists when it came to the Pagodroma and Sirius Tillites, diatoms, is that you can change the 10,000 year Antarctic deglaciation based on cosmos, which we've done plenty of, push it to 14,500 years. But then when you do the ice elevation loss factor, and you try to integrate what ice mass loss there would be, it doesn't add up to the 20 meters that's missing in meltwater. That's observed, or actually 15 to 20 meters, that's observed in the 500 years of meltwater pulse 1A. And that's an important point. Even if you did manipulate the cosmo ages and put them at 14,500, I believe, you can correct me, most of the modeling and the integration or the extrapolation of the modeling at certain sites for ice sheet loss to add to global sea level, it doesn't come anywhere near the 20 meters, but maybe 5 or 6 meters. I mean, that's what I knew as a status through Dwayne's work and others. Dwayne may want to comment on that.
Yeah, I mean, yeah, I guess the meltwater debate is kind of getting further from the main focus of this talk. But yeah, I agree there's still that gap there. In fact, kind of attending AGU this week, which is why I feel slightly sleep deprived at the moment. There's been a couple of talks that also actually show that there's perhaps some missing ice from Scandinavia that wasn't really considered before that could close that gap on water pulse 1A. Yeah, we'll leave that.
Okay, thanks a lot.
Discussion.
I have a question, Richard.
Go ahead.
Is it possible to incorporate this isostatic adjustment and even atmospheric effects in a calculator for calculating from samples to exposure ages or erosion? Would that in principle be possible?
Sorry, can you say that again? You were breaking up a little bit for me.
Okay. So, so most of us, we're using calculators to derive from our values, exposure ages, etc. And these models, they assume no isostatic adjustment, I presume.
Yeah.
Would it be possible in the future that all these things get quantified enough through your projects, for example, that can be incorporated in the calibrator?
Yep. Yeah, so as I kind of highlighted at the end, on the ICE-T website, that's got several tools, and one of those actually has an online exposure age calculator, where you can actually calculate your exposure ages with GIA correction. But the purpose of that is just to give you an idea of the potential impact on your samples. I wouldn't say that you should take that as a matter of fact, those exposure ages, because like I said, there are still uncertainties in exactly what this is, what the kind of, the absolute effect will be, especially when you take account of atmospheric pressure changes. But it's just to give you an idea at this stage. But yeah, I agree, hopefully in the future, we can have some calculators that fully account of GIA and the uncertainty in the GIA estimates, as well as atmospheric pressure change. I had hoped to get that up and running now, but I'm waiting on Nat Lifton's exciting paper that will hopefully come out sometime soon, and I'll build on that.
So I had one quick question for you as well, Rich. How well does ICE6G capture kind of what's going on with the ice sheets, with both the Laurentide and the Fennoscanian ice sheets in the Northern Hemisphere? Does it do a pretty good job? Or?
Yeah, I think it does a better job than ICE5G.
Okay.
I don't think Scandinavia is too different, but North America, there's actually quite a big difference between those two models. And so for the ICE-T correction, I actually include ICE 5G and 6G, so people can have a look at the difference. And North America is one of those areas where there is a difference.
Yeah, I was eyeballing specifically where the courtier and ice sheet should be, and that was kind of strange. And then looking kind of the time slices, it got kind of weird. That's what I was asking.
Yeah.
If that actually does capture it pretty well.
Yeah, there's also Lev Tarasov's group. There's a lot of ice sheet GIA models from there, which I hope to include in that GIA correction as well.
Nice.
I have a question. I'm just thinking on it. So, so you mentioned some erosion rates at the beginning of your talk, and I was wondering, have you tested what is the effect on the erosion rate?
No.
No.
So like I said, when I did this, I was mainly focused, and I guess most of what I do is focused on kind of surface exposure ages, and yeah, that's where all the focus was. And we don't talk. Maybe I mentioned in half a sentence erosion rates in the paper, but that wasn't the focus. But actually, yeah, talking to other people, particularly in this group who do other work with erosion rates, I do start to wonder what the effect is there. But I haven't got. I mean, if you're interested, it might take me a little bit of time, but the code is all there. And if you go to the paper as well, all the calculations and like the ICE-T code is all built on the Cronus calc MATLAB code, and it's all the scaling models have been changed to account for elevation changes. But I've written that at the moment just for surface exposure. Yeah. But actually, it's just the end bit really. I just need to substitute some of the code around, and then can have a look at erosion rates. But yeah, to answer your question, I haven't looked at it in detail.
Yeah, because I was thinking now while you were talking, so I don't know how good is my suggestion, but I was wondering if you could test your model on an active landscape where you have also GPS data and some maybe in Himalaya or Taiwan, where you have also cosmo rates mainly. I don't know how many ages, but you also have GPS data. So basically would you be able to test it on millennial scale, the change? Or
yeah, I mean, in terms of the GPS data, do you mean just look at it locally using the effect from GPS data?
Where they measure the uplift rate independently and knowing the uplift rate, and then having the rates or dates depending, availability, and just investigating the last, 1,000 years or so, because they do extrapolate those uplift rates to a certain age. So what is the effect on the cosmo cosmo ages of the change?
So I guess there's two aspects. There's those sites, the erosion rate studies that are close to these continental ice sheets or these former continental ice sheets. So like I said at the beginning, there's some sites in Europe and North America, and they might be interesting to have a look at those. And then, as you say, there are these other sites further away from the continental ice sheets, where there are still fairly significant elevation changes, although they wouldn't be as significant as the GIA on these glacial interglacial timescales. But that would still have some effect. And I haven't got the calculator working to actually calculate the erosion rate difference. But on ICE-T, like I said, you can put in a linear rate. So perhaps if you have some local, or if you have some information about uplift rates from local GPS or something, or whatever, and you can plug that in, and then it will at least let you know the difference in production rate, and then you could have a look how that difference in production rate may relate to your erosion rates. But I haven't got the next step in terms of then correcting the erosion rates set up.
Thanks.
And for anybody who's interested, I put the website for ICE-T in the chat, so definitely have a check or have a look at that. I found that quite useful for my own work.
I'm a bit confused about what this erosion rate business is, because are we talking about the connection between changing erosion rate as a function of atmospheric elevation, because you have different chemical weathering or physical weathering at various elevations as the GIA takes account? Or are we talking about, let's say we have an erosion rate of 1 or 2 millimeters per kiloyear, and it's not accounted for because the age calculations are based on 0 erosion rate. And if you want to throw erosion rate in over 15,000 years at 1 or 2 millimeters per kiloyear, like typical cold temperature environments, that wouldn't do more than a few 1 or 2%, 3% on your effect if it was transferred to production rather than to erosion. So I'm not quite sure if you're talking about erosion changes as a function of time due to elevation changes, or enhancing your corrections by including erosion rate as a constant value for some arbitrary independent number like 2 millimeters per kiloyear, and see how it affects your GIA effect. Is that what we're talking about?
I mean, I was kind of thinking more of, your calculations of erosion rates are dependent on your production rate. And if your production rate has changed through time as a result of elevation changes, then your estimate of erosion rate will be affected.
Yeah, but that if you're giving 2,000 years out of 15,000 years, or let's say, right, you're giving a 10% effect, your erosion rate is linear when it comes saturated. When you're at steady state, your production rate changes and your erosion rate changes have to compensate to give you that measured concentration. So if you've got a 10-20% change in exposure age calculation due to GIA, and you want to transfer that to erosion rates, that's only going to change the erosion rates by the same amount, 20%. Because you have to assume steady state to work out your erosion rate. Yeah, you've got to assume that your concentration is either erosion independent, 0, which gives you the kind of minimum age, or you work the other way and you work out so if you do both, if you put erosion as a variable and age as a variable, then you're really screwed up, because you can't control the effect of GIA on your production rate, because you don't know what the erosion rate is. So if what you're saying is what you're worried about, I think the bottom answer is back of the envelope calculation. That if your age has changed by a certain fraction and you want to transfer that to an erosion change, that's the same ratio, effectively. I would think, just offhand from the formulas. But anyway, I don't think it's a serious effect, put it that way. Yeah. I thought you had more to do with the fact that erosion changes with elevation, not because a production rate changes, because at higher elevations, you have a different regime of erosion, which is well studied in some of the Antarctic environments. You have kind of like weathered zones and non-weathered, or maximum weathering limits and non-weathering limits. It's like, oh, don't worry, we can do that offline.
So yeah, with that, we're running out of time. So maybe I'll put it over to Aidan to kind of go through a couple of housekeeping items.
Yeah, some of it can probably end up in an email if we want to cut it short, Ross. But just to note that the next speaker will be Rekha in January on the 28th. I don't know, Rekha, do you want to give a little preview of what you're going to talk about next month?
No.
No? Okay.
It's a secret. I don't know. I have to decide what do I talk about. Do I talk about the sediment or some other research which you're doing currently? So I haven't decided yet. So I will send something around Christmas to Ross, and he can distribute.
It'll be a surprise. Oh, well. Yeah, so the other things we had were just the website is progressing. I think it's nearly there, right?
Yeah, Rich has done a really good job with that. We all owe him a debt of gratitude.
Yeah, for sure. And we are still we are discussing and trying to work out whether a meeting can go ahead. But we don't really know whether people will have the capacity to do it in the next, say the first part of next year. We were initially thinking when we discussed it that it would be 2022. And now given the current circumstances, I think 2022 seems reasonable, but I know there is some intent from people in this group to have it sooner. But so we'd like to gauge the group, whether they think there's capacity for people to have an in-person meeting early next year, or to push it out to when things have settled down a bit. But yeah, no need to discuss this now because we're running out of time. So.
All right, well, thanks. Thanks again, Rich. Let's all give him a hand. It was a very, very good talk. And with that, we'll see everybody in about 6 weeks or so.
Yeah, Merry Christmas, everyone.
Happy holidays. Yeah.
Have a good holiday, everybody. Get some fun things done.
Yep. Thanks for the talk, Rich. Really good. Enjoyed it very much.
Likewise. Merry Christmas, everyone.
See everybody.
Take it easy, folks. I wonder if Steve is still there. Are you still there, Steve?